Hello everyone, I am L. Janardhan, an electronics and computer engineer from VIT Chennai. I am doing a presentation on a study on Turing machine and its application in the subject Theory of Computation under Saravanan P. Sir. So before going into the introduction of a Turing machine, let's try and visualize what a Turing machine really is. So we see every day around us that there is so much technological advancement. We see that our phones, our laptops, our computers are getting updated every day. We see new and new updates coming every day. But what if I say all the computation that we can do from our computers and laptops today could be done in 1936 using a simple automata? Yes, we have definitely gotten faster, we have improved the speed, and we have gotten more efficient, but we are still doing the same computation that could be done in 1936. Yes, the automation I am talking about is Turing machine. Turing machine is an automata that could decide what a computer can do and cannot do. And all the computers invented even today, even the modern computers still follow the same automata. So it was started by a thesis of Alan Turing. This is a photo from his own research paper that says it is possible to invent a single machine which can be used to compute any computable sequence. And the single machine that he discovered later was the Turing machine. So let's get to the definition. A Turing machine is a finite automaton that can read, write and erase symbols on an infinitely long tape. The tape that is given here is divided into squares and each square contains a symbol. The Turing machine can only read one symbol at a time and it uses a set of rules to determine its next action based on the current state and the symbol it is reading. So here is some more definition about what a Turing machine is. In the context of automata theory and the theory of computation, Turing machines are used to study the properties of algorithms and to determine what problems can and cannot be solved by computers. Just like I said, the Turing machine can be helped to find out what algorithms can be performed and cannot be performed. They provide a way to model the behavior of algorithms and to analyze their computational complexity, which is the amount of time and memory they require to solve a problem. Thus we can calculate the time complexity and space complexity of algorithms using Turing machine. The Turing machine's behavior is determined by a finite state machine, which consists of a finite set of states, a transition function that defines the action to be taken based on the current state and the symbol being read, and a set of start and accept states. The Turing machine begins in the start state and performs the actions specified by the transition function until it reaches an accept or reject state. If it reaches an accept state, the computation is considered successful. If it reaches a reject state, the computation is considered unsuccessful. Now let's see a diagram and try to understand it in a better way. So let's imagine this as the infinite tape of Turing machine, and this is what we call head in Turing machine. So let's think that head is kept on a specific square. Now the head can read, write and edit whatever is written here, and it can also move left or right based on the instruction that we give Mr. Head. So in short, Turing machines are an important tool for studying the limits of computation and for understanding the foundations of computer science. They provide a simple yet powerful model of computation that has been widely used in research and has had a profound impact on our understanding of algorithms and computation. Now that we have seen so much about Turing machine, we must be thinking that who invented this Turing machine? No prizes for guessing, as I have already mentioned that Alan Turing invented Turing machine in 1936. He is widely considered to be the father of theoretical computer science and artificial intelligence. His contribution in computer science are so big that the biggest prize in computer science field is called the Turing Prize. All the modern computer science that we even use today is all because of his intelligence and hard work. Now, if you are wondering how a Turing machine hardware looks like, it looks like this. This is the infinite tape that we have been discussing about, and this is the head that is pointing to a specific square. Now, let's try and visualize how a Turing machine works. The Turing machine operates by performing the three basic operations that I mentioned: read, edit the symbol or write a new symbol, and move left or move right. Now let's see a demonstration of its working. Let's try printing the number 110 using a Turing machine. Now first we'll initialize the head, that is, we'll put the head on a specific square that we want. Now we'll input the first number that we want, which is 1 in this case, and then we'll move the Turing machine towards the left, and thus the head will move towards the right. So move the tape towards the left, and now we give the next input, which is 1, and now we do the same and give the next input, that is 0. Now we can do anything using the same concept. For example, we could reverse it, that is, we could go to the left, and for example we could do something like reversing the bits, convert all zeros to 1 and all ones to 0. So then it will become 1, here 0, and here 0. So 0, 0, 1 would be the new input. The definition of Turing machine according to theory of computation is given as a 7 tuple. We know that finite automata was a 5 tuple. So let's see what are the components of a Turing machine. Q is the finite set of states, X is the tape alphabet, sigma is the input alphabet, delta is a transition state, Q0 is the initial state, B is the blank symbol, and F is the set of final states. Let's see the time and space complexity of a Turing machine. For a Turing machine, the time complexity refers to the measure of the number of times the tape moves when the machine is initialized for some input symbols, and the space complexity is the number of cells of the tape written. Time complexity is order of n log n, and the space complexity is order of n. Let's compare Turing machine to push-down automata. We know that push-down automata has only one tape of fixed length, while Turing machine has infinite tape. Push-down automata has stack as the memory, that is, it has limited memory, and Turing machine again has infinite memory. Push-down automata has a less powerful computational power than Turing machine. Turing machine accepts all languages, while push-down automata only accepts context-free languages. Turing machine is deterministic, and push-down automata is non-deterministic type of automata. Now let's check Turing machine for a language A power n, B power n. So the language is A power n, B power n. Let's take n equal to 3. So we'll get A power 3, B power 3, which is A, and B, B, B. So let's input the same as we saw in the demonstration. We'll bring the head here and input the first element, which is A. Then we take the head to the next position, input the next A, then B, B, and B. So Turing machine works like, we put the head, that is the first state Q0, here, and what we do is to check if number of A's is equal to number of B's, that is, if A power n and B power n, the n is same, we will first check the leftmost element of the first character. That the first character here is A and the second character is B. So of the first character A, we will check the leftmost element and convert it to X. So if for Q0, if we find A, we will convert it to X and then move right. Now we come here. So for Q1, when we have A, we will just skip it and go to the next. So we will go here and it's still the same. So it will skip this A again and go to B. Now we have a new character. So for the new character, we will convert this B into, say, Y. So B gets converted to Y. and we'll shift right, and we'll skip all the B's till we find a new character. But as here there are only two characters A and B, so all the empty squares can be written as blank B. So as there are only two characters, it will reach blank and then start moving left to the new leftmost first character, that is this, and it will convert this to X. Now it will go here, convert this to Y, do the whole process and then come back here, convert this to X again, go back and convert this to Y. So now we have B, XXX, YYY and BBB. So there is no mention of small a's and small b's. So when the Turing machine gets converted to only B, X and Y's, we know that the language is a part of the Turing machine. Now we'll see some applications of Turing machine. Alan Turing also gave another thesis called the Church-Turing thesis, which says that every solvable decision problem can be transformed into an equivalent Turing machine problem. Which is what I said in the beginning of the video, that if there is a computation problem and if it can be solved by the computer, it can definitely be solved by the Turing machine. So that also means that if something cannot be solved by the Turing machine, it cannot be solved by the computer. So when computer scientists sit and write algorithms, so they can first check if it works in a Turing machine, if the problem can be solved using Turing machine. If it can be solved, then there must be definitely an algorithm that can be made. But if it cannot be solved, there's no way that you can make an algorithm to make it work. So before starting the work, we can check using Turing machine that if it's solvable or not. That is what we call checking decidability. Now that we know if a problem is solvable or not, now if we get all the solvable problems in one set, we can again divide it into two parts. Everyone who knows who has studied algorithms knows that algorithms can be divided into two parts: the P and NP, or class 1, class 2, which is easily solvable ones and non-solvable ones, which can be tracked and which cannot be tracked. So the easily solvable ones, which have less time complexity, we can also find it out using Turing machine that if the problem is easily solvable, if it has time complexity in the order of in polynomial time or in exponential time. And it can also be used in implementation of neural networks, implementation of robotics application, implementation of artificial intelligence, and it is used in artificial intelligence as a model for learning and decision making. It is used to study the relationship between classical computing and quantum computing. It is used in digital circuit design to model and verify the behavior of digital circuits. Thank you.